In this video, we will derive Euler-Lagrange equation using method of variational calculus. So suppose for a physical system, we have Lagrangian, which is usually defined as kinetic energy minus potential energy, and is also a function of Qi's, the generalized coordinates, their time derivatives, and time. So looking at the state space of the system, Q, I's and T, suppose we have defined the state of the system at some time T and some other time T2, T1 and T2. So our aim is to find the actual physical path that the system would take to go from T1 to T2. So for this purpose, let us define something called the action, defined to be T1 to T2 integral of L dt. And Hamilton's principle states that the actual path that the system takes, let us say S tilde, to go from sometimes say T1 to T2 is such that it is the extremum point or extremum value of the action, which means the slight variation of S at that path is 0. That Qis S achieves its extremum, and S is a functional. A functional is the function of a function. So Qis are the function of time, and action S is function of Qis. So S is a functional. Now let us begin the mathematical manipulations. We have variation S. The slight variation in S is 0, which implies delta integral T1 to T2 L dt equal to 0. This can also be written as T1 to T2 delta L dt is 0. Now let us assume that Li is a function of only one generalized coordinate, its time derivative, and t. Function is taken without the loss of any generality, because at the end we would see that the result which holds for just one coordinate is also true for a set of coordinates. Now we have delta L is equal to dou L by dou Q delta Q plus dou L by dou Q dot delta Q dot. We are not considering dou L by dou T because the change in L is due to variation in Q and not T. Tildes here because this is for the shortest path. Q tilde denotes the shortest path for which the variation in S is 0. Now we have, so this implies integration T1 to T2 delta L will take from here dou L upon dou Q tilde delta Q tilde plus dou L upon dou Q tilde dot delta Q tilde dot dt. This must vanish. So we have So we have this integral. Now let us label this part as second part of the integral. So second part is integral t1 to t dou L upon dou q tilde dot delta q tilde dt. Here in this we will use integration by parts. So say if we choose this to be our first function, this is our second function, and use the technique of integration by parts, this would give us dou L upon dou q tilde dot integration t1 to t2 dou q tilde dot dt. This is dot here, minus of integration t1 to t2 d by dt of dou L upon dou q tilde dot and q tilde delta q tilde dt. So this implies the first term is dou L upon dou q tilde dot delta q tilde t1 to t2 minus t1 to t2 d by dt of dou L upon dou q tilde dot delta q tilde dt. Now since we had fixed a system at t1 and t2, so the variation of q at t1 is 0, and it is also the variation of q at t2, which is 0. So this implies this term goes to 0. We are left with minus of t1 to t2 d by dt dou L upon dou tilde dot delta q tilde dt. So this was our second expression from this quality. Now we will plug in the value of this term back into our original equality. So we'll have integration t1 to t2 dou L upon dou q tilde delta q tilde minus of d by dt dou L upon dou q tilde dot times delta q tilde, and this is 0. Now take the delta q tilde out of this square bracket, so this would become delta q tilde times dou L upon dou q tilde minus d by dt of dou L upon dou q tilde dot dt equal to 0. Since the variation in q tilde is arbitrary, we must have this term in the square brackets should be 0. So this should be 0 because this whole integral is 0 and the variation in q tilde is arbitrary. So the term in the square brackets must be identically 0 for this to hold true for any arbitrary variation in q tilde. So the expression defining q tilde that we solved is this: q tilde dot is 0, and this is the Euler-Lagrange equation. So any physical system you take and you define its initial and some final position or final configuration at time t1 and t2, and if you seek to find the path that the system would take, then the path qt should satisfy this Euler-Lagrange equation. So that's it, we got the expression we were looking for. So that's it, and if you have any doubts regarding any of the steps, you can mention that in the comment box below. I'll try best to resolve it. Thank you.